Welcome to the session on selection. My name is Andreas. I'll be sharing. We have 3 papers in this session. And the first paper is by Bret, Kayla, Beckham, Anael, Kuperwajs, Cohen, and Brianna, Heggeseth, all from McAllister College in Minnesota. And Bret will be giving the presentation.
So thanks for that introduction. I want to make a specific note that this work was done at McAllister College, which is a small liberal arts college in Minnesota, about 2,000 undergraduate students. So particularly for any of the PhD students in the room, if you're interested in knowing what it's like to teach and do research at smaller institutions, feel free to come talk to me after the talk. And this work was done with 2 of my undergraduate students, Anael and Kayla, as well as one of my colleagues who's a statistician, Brianna, Heggeseth. So the focus of our paper is on region of interest selection techniques for use in immersive environments. And in particular, these types of techniques are critical in many different domains. So for example, in 3D modeling, it's fairly a common exercise to try to select some region of the model to be the focus of future modeling operations. And the data that's contained in that region may or may not correspond with triangle boundaries, for example. So this is some of our prior work in this area, selecting a region of interest in surface geometry on, this is a roof of a cultural heritage model that you might want to actually annotate. These types of interfaces are also used in, for instance, scientific visualization. It's fairly common to want to filter down to a smaller subset of the data that maybe you want to perform more analytics on, or just to adjust your viewpoint. And so it's important to look at how we might select these types of regions of interest. And this brings us to our prior work. So Bærentzen et al. In 2019 created this extended taxonomy where they included a lot of different papers on single object selection. So for example, sort of fairly typical raycast type selections, spotlight techniques, as well as techniques that will select multiple full objects. But then they also distinguish based on the target for region of interest ones, and I'm just showing those here. Actually, the 3 bottom bold ones are ones that were missing from their taxonomy that I've added here to try to make it a little more complete. They also distinguish these based on how the region or the shape of the region is created, and whether or not it's a fully manual approach, using a 3D user interface, or whether it has a more semi-automatic approach. So the first 3 you see on the top there, so cylinder selection, cloud lasso, and cast, were all techniques that are semi-automatic. The user somehow, maybe they draw a lasso or adjust where a cylinder is in space to select sort of an initial selection, and then based on the underlying data, in this case these were all for point cloud data, they could look at things like density to expand that region to match the data. In contrast, we're a little bit more interested in fully manual approaches because they are more generalizable to a wider variety of data. For example, the 3D modeling application that I mentioned. So I'm going to talk specifically about the 4 techniques you see on the bottom, tangible brush being the first one. So the way that tangible brush works, this comes from Tobias Eisenberg's group at INRIA, is that it essentially has a 2-step process. So the user is using a Google Tango tablet that's tracked in 3D space, and they draw an initial selection in 2D, a lasso essentially. You can see that over here. And then by physically moving the tablet through space, it extends that initial drawn outline into a 3D volume. And in this way, you can select non-convex, fairly complex regions of interest in the scientific data that you're looking at. The second technique comes from Ulinsky et al., and this was called volume cube, and it uses a box metaphor. So this was, the reason it's called volume cube is they were selecting volumetric data, and essentially whatever's inside the box defines your region of interest that you're interested in selecting. And they defined 3 different methods for controlling that box. And the one that had the highest accuracy is what's referred to as the 2-corner method. So in this method, you can sort of see this in the picture here. There's a little ball at the corner, opposite diagonal corners, and your hands essentially control those. So you can scale by moving your hands apart, translate by moving them together, or rotate based on the relationship between them. The third technique is slice and swipe, and this comes from Doug Bowman's research group at Virginia Tech, and it was in response to the 2014 3DUI challenge. I don't know if any of you guys participated. The goal of this challenge was to annotate 3D point clouds. And so the way that this particular technique works is using the leap motion controller, you can see on the desk there. The user would use their finger like a chef's knife metaphor, essentially cutting the data. So a quick slicing action would create a slicing plane through the data. And then by swiping perpendicularly to that initial cutting plane, you would essentially sweep the data away in the direction of your swipe. And so by making repeated cuts and then swiping away the data, you could narrow down to a region of interest. The last technique comes from my prior work, and it's an interface that we call Yea Big Yea High. And the idea is that you have essentially two infinite cutting planes attached to each hand. Excuse me, one for each hand, two of them in total. And they're oriented to point towards the other hand. So you're essentially just controlling the position with each hand, and then the relative positions between your hands adjust the orientation. And the space in between defines the region of interest. So you can move your hands around, lock them into a particular space, and then you have essentially this long corridor of selection. And you can repeat that process. So you might say, I want it yay big, and select horizontally, and then yay high, and it would then progressively refine to sort of a long cube, and you might then select in depth as well. So we found these four techniques, and we were actually a little bit surprised there were only really four that we could identify that do region of interest selection in a manual way. And we were interested in evaluating their relative benefits. And so we looked in the literature, and we found that there are a lot of evaluations for doing single object selection, where you want to select maybe a full table or a chair. And even multiple object selection, maybe use some sort of frustum volumetric selection, just like multiple objects. But there weren't any really systematic reviews of region of interest selection methods. And so that's sort of this gap in the literature that we're trying to fill here. So we designed a study. It turns out we decided to only actually compare the last three of the interfaces. So we left out the tangible brush because it used this extra tablet. There wasn't an easy way to adapt that to kind of conventional VR headset hardware. The other big difference between it is it allows non-convex selections, whereas all of the rest allow convex because they use infinite cutting planes. So we'll leave it to future work to try to compare that. I'll talk more about that in a bit. The particular application we were interested in was selecting surface geometry, again, thinking about 3D modeling application. And so we implemented all of the techniques, and there are a few different details here. The first is that for volume cube, to try to make a little bit of a fair comparison, we allow you to do progressive refinement. So rather than just being limited to a box region of interest, you can select a box, reposition it, and select again. And we essentially take the Boolean intersection of those selections so that you can start to define more complex regions of interest. And then for slice and swipe, again, it was originally designed with the leap motion, but we adapted it to use a HTC Vive controller. You can see in the pictures here, we essentially display a 1 meter long knife, if you will, that the user can use to slice through the geometry. We recruited 19 participants. It turns out we had some hardware issues with the very first one. They weren't able to complete most of the trials, so we disregarded their results. So our final results had 18 participants, roughly university student age, and I would classify all of them, almost except for two, as really novice VR users. There were two that had more than 20 times, but most were less than 5. We used an HTC Vive with the standard controllers, and running on a fairly modern PC with Unity. And the participants had a roughly, slightly less than 2.5 square meter area to walk where we calibrated the floor. We did make sure that we started them all at the same position for every trial to try to avoid navigation time being a factor in the selection time. So the task. The participants were presented with 7 different models, and each model had a blue subset, see that here? And their task was to select that subset as quickly and accurately as possible. Essentially, the subset was the region of interest. the models essentially were in two different categories. You may have this experience in designing these types of studies. You have to simplify it enough that the participants can actually complete the trials in a reasonable time, while hopefully not simplifying it too much. And so we had 6 what we call synthetic data. There were 3 different target shapes, so a circle, an irregular polygon, and a rectangle. And we looked at those both on a cylinder, so thinking about how you select on curved surfaces, as well as a flat plane. And then we were interested in kind of a more real-world example with dense data, and so we used the hemoglobin molecule, and the participants were asked to select the oxygen binding site at the center of it, so slightly more complex. They trained on 3 additional models that aren't shown here, and to make sure that they actually were proficient, they had to meet 80% precision and recall, or else they had to repeat those training trials. And in general, the training time on average for Yea Big Yea High was 4 minutes, and 6 minutes for slice and swipe and volume cube. We used it within subjects design, repeated measures, so they used all 3 trials, all 3 interfaces, and all 7 trials. The interfaces were fully counterbalanced to try to avoid learning effects, and the models were randomized, except we did do M7 last for each interface for every user. Our dependent measures were time as well as accuracy, and so for accuracy, we used 2 different metrics, the F1 metric, which is frequently used in information retrieval and combines precision and recall. And these are based on the area of selection, is how we define true positives and false positives, for example. We also used the Matthews correlation coefficient, or the MCC, which adds the true negatives as well. And so it balances a little bit more for when you have cases where you have uneven areas. So for example, here the target selection area tends to be a lot smaller than the non-target selection area. And both of these metrics have been used in prior work to facilitate comparison as well. We also looked at workload and perceived exertion, and so we used the NASA TLX as well as the Borg CR10 questionnaires. Okay, for completion time, this table actually has all of our results on it. Mostly what I wanted to draw your attention to is the last column here, the completion time. And this is subdivided based on the particular interfaces. The first thing to notice is that the real-world example, that molecule M7, shown here, tended to be about twice as slow as the more synthetic data. And that's actually not surprising. It had a little bit more navigation because users wanted to kind of look around and see all the different dense parts of it. And the selection target was a little bit more complex as well. For the synthetic data, so the models M1 through 6, on average for Yea Big Yea High took about 48 seconds to select, 60 seconds for slice and swipe, and 65 for volume cube. This particular chart is showing the model-adjusted mean differences between interfaces. And you can see from it that completion time was significantly faster for Yea Big Yea High compared to both slice and swipe and volume cube. So if you're, in this case, subtracting a smaller number, right, your chart is going to be further to your right. There were a few other things to note. Square targets were significantly faster to select than circles and irregular targets. Again, not surprising, right? Both circles and irregular targets needed more selection operations to try to basically define the edges of the target. Interestingly enough, irregular targets are faster to select than circles on cylinders, but we're slower on flat surfaces. So I'm not quite sure what's going on there, and that needs a little bit further study. For accuracy, both the F1 and the MCC were really highly correlated, so I'm going to pretty much talk about it only in terms of the F1. What we found is that Yea Big Yea High was significantly more accurate than either of the other 2 interfaces. Again, you can see the model-adjusted differences and 95% confidence intervals there. One thing to note here, though, is that actually if you look at all the values, right, they're all pretty accurate. They're in the 0.9 region, and so that's a good thing. All of these are actually pretty good selection interfaces. Just Yea Big was slightly more accurate. In terms of workload, the top table is showing the weighted NASA TLX scores. And again, Yea Big Yea High had basically the lowest workload, followed by slice and swipe and volume cube. These box plots here are showing the raw subscores, and we found that participants rated both slice and swipe and Yea Big Yea High much lower on the mental and frustration scales. There weren't clear differences, however, in the temporal scale, which is a little bit interesting, even though there were some differences in time. In terms of perceived exertion, we used the Borg CR10 scale. This is a 1 to 10, where 1 is almost no effort and 10 is like the most strenuous exercise you've ever done. In this case, perceived exertion for all of the interfaces was fairly low, but volume cube actually corresponds with moderate exercise. In our qualitative results, participants ranked their preferred interface as Yea Big Yea High, as well as being the most accurate and most comfortable, and that in all of those categories was followed by slice and swipe and then volume cube. All right, so some lessons learned and discussion from this. Why did we get these results? What we found is that Yea Big Yea High was the best for accuracy and speed, but that could be explained in part because of the strategies that participants used. And so with Yea Big Yea High, we essentially have two cutting planes that you can somewhat independently move. And we noticed that 11 out of the 18 participants, when they were making selections of square or circular targets, would actually essentially cut both edges of the sides of the square at the same time. Right? So you could essentially, if you were perfect, select a square in 2 operations, right, with Yea Big. Whereas the other techniques you would need to do, potentially 4. For slice and swipe, we also noticed kind of an interesting phenomenon. Participants would not try to be precise to begin with. They would just make large cuts to get rid of extraneous geometry, and then they would go back and make cuts that were much more precise to try to narrow in on the edges of the region of interest. We also noticed that because slice and swipe, in order to activate it, you have to move your hand above a certain threshold. That adds a little bit of inaccuracy, which could explain also the accuracy results. And we noticed that just like you might pre-plan a golf swing, participants also did this. They would move their hand kind of slowly along the edge of whatever region they were trying to cut, and then eventually when they felt like they were kind of accurate to where they wanted to be, they would speed up to actually get above the threshold and make the cut. Interestingly, 12 participants perceived slice and swipe as the fastest, even though it was slower than Yea Big Yea High. And we attribute that to kind of the game-like effect of this interface. Right? It's a little bit like Fruit Ninja. Many participants actually rated it as pretty fun. And so as you think about designing interfaces in this style, that might be something to think about. Do we actually care that you're the fastest, or do we care that you think you are the fastest? The other reason for these results is that Yea Big Yea High's increased accuracy might be explained in part by the more limited degrees of freedom. So it is a 6-degree of freedom interface, but that's divided to 3 degrees for each hand, because you're essentially just controlling the position of the planes, and then the relative position between your hands defines their orientation. And so those more limited degrees of freedom compared to slice and swipe, where it's a full 6 degrees of freedom, could explain the accuracy. Interestingly, we would have expected similar results for volume cube. It again has 6 degrees, but it's split to 3 for each hand to display essentially the corners of the cube. But that may have been overloaded by a higher mental load. So what do I mean by that? Well, we found that increasing the number of cutting planes tends to lead to higher mental load. I'll give you a second to read this quote here by one of our participants. Essentially, one of the issues with this is, even though with these techniques, and we did see this with many participants, you could essentially select both sides of, let's say, the rectangle here at the same time, many participants tend to only focus on one hand at a time. Right? And the problem with that is that works just fine as long as your other hand is wide enough away that it's not constraining the selection on this edge. Right? And so what we found here is that for Yea Big Yea High, occasionally participants would be focusing on, let's say, their right hand and make a selection, but their left hand was within the region of interest, the target that they were trying to select, and so it actually cut part of it away, and they'd have to undo the operation and try again. And that became even more extreme with volume cube, which I think explains why it was more frustrating to users. Many only focused on what seemed like one or two sides of the planes of the box at a time, and then you had to actually keep all 6 planes in mind to make sure you weren't cutting something away that you didn't mean to. But the box actually does have some advantages. So for our last model, the real-world molecule example, we found that volume cube actually had the highest accuracy and fastest time for that model. And that's likely because its cutting planes are really constrained by the edges of the box. And you can see it right in front of you. Whereas Yea Big Yea High and Slice and Swipe used infinite cutting planes. And what we found is that, for instance, to select the region here, you have to make a side selection and a top selection, but you also had to select in depth. And there's been some prior work that's found that depth perception and moving in depth like that with your hands tends to be a little bit slower. Whereas with volume cube, you get that essentially automatically, because all you had to do was just stretch the box around that region. And so for particularly dense data, this might be something to consider, where volume cube might be a better approach. We also noticed that performance probably depends a lot on visual feedback. So our implementation of Slice and Swipe used this sword, and we found that it seemed to work best for really rough cuts, but users had a lot of trouble trying to get it to be precise in their cuts. The other thing we noticed is that they tend to focus on the tip of the sword rather than their hand, and the activation threshold we used for the hand movement was based on the hand, not the tip. And so early in some of the training trials, we noticed participants would focus on the tip and they would just rotate their hand rather than translating it. And that didn't actually activate the technique, even though the tip of the sword would move quite a bit. So future implementations should probably take that into account and be based not necessarily just on the hand, but also the end of the sword. Finally, one of the most interesting results is that users tend to favor selections with more false positives. So we didn't actually define what we meant by accuracy. We just told the participants be as quick and accurate as possible. And we noticed that the majority of the participants preferred selecting regions of interest that were larger than the target area. So you essentially have more false positives within that shouldn't have been selected. By and large, when we looked at the number of undo operations that users performed, most of the time that happened when they made some selection that excluded part of the target region. Even if it was a very small amount that was excluded, and in fact might have been globally more optimal than their next approach that had way more extra non-target area included in it, they still seem to prefer it. So future interfaces for region of interest selection might want to take this into account. We did have several limitations. One being Slice and Swipe was originally designed with the leap motion, and in that context, where you're making small finger motions rather than full hand motions, it probably would have been more accurate and certainly have lower fatigue. We also had to limit the complexity of the models in order to have a reasonable time for the participants to complete all the trials. And then finally, the selections here are all limited to convex regions of interest. As opposed to, for instance, tangible brush, which allowed non-convex regions. And so this is an area of active future research. I think we need more non-convex selection region of interest techniques. So finally, we presented the first evaluation that compares multiple region of interest selection techniques using conventional VR hardware, and we've just discussed a few design decisions for future work. There was a small error in the proceedings, and our PDF is not actually up in the proceedings yet. As they get that figured out, if you'd like a copy, it's listed on my website there. And I'd be happy to take any questions.
So really interesting, thank you. Perhaps I'm wrong, but doesn't the extension you made to volume box, would that not allow non-convex selections as well?
I don't think so, because we were doing a Boolean intersection test.
Okay.
And so, yeah, because it's a Boolean, right? You could potentially implement it in a way that it would allow non if you did, a union intersection or something, or subtraction essentially.
Okay.
But I think because it's a Boolean operation, it doesn't.
I'm curious about a couple of things. So the selection targets are, in my mind, mostly a little bit flat, right? Except maybe for the molecule. And I'm just wondering whether that might influence the results.
It's possible, yeah. I think in some ways that's why with the dense data set actually volume cube did better. I think that might be one of the limitations, is that we made it so that all of the targets didn't actually go onto the backside of, for instance, the cylinder. In fact, it's actually just a half cylinder because we didn't want users to accidentally not realize they were selecting things on the opposite side, and we didn't want them to have to walk around to do that. One of the training sets was essentially a figure 8 torus, 2 tori together, and that was sort of similar in a way, in that you had to make one sort of selection this way and then one in depth as well. And yeah, I think it's something to consider, certainly with future work. There's always that trade-off in trying to simplify it enough, right, without too simple, and we might have gotten a little too simple in some of these examples.
But continuing, if you, I think that you report these rather high numbers, and I guess to some extent, isn't that also because there's a lot of stuff not to select? So
right.
you would get a pretty good rate if you have sort of like a reasonable approximation.
Mm-hmm.
And that leads me to think that maybe one way to test your method that would also perhaps deal with the fact that you don't want to cut into the selection set would be to have sort of like a region in which the selection is supposed to lie, or these spreading things are supposed to lie.
Uh-huh.
I don't know if
Yeah,
you
that would be interesting. I think in some ways it's application dependent, right? So, maybe with instead of surface geometry, let's say we were doing point cloud data. Maybe you only care that what is in the region is something you're interested in, but you don't care about all those extra sort of false positives.
Yeah.
In that case, actually a box selection is probably going to be the quickest, because you just scale it to take whatever big data. It doesn't matter how much extra stuff is in there. But yeah, that's interesting to think about.
More questions?
Yeah. Did you collect statistics on the undo operations? We did record them, but I'm not sure. We didn't actually ever run any statistics on them. I think that might be interesting.
Yeah, I think anecdotally, from my recollection, the volume queue had the most. Actually, no, sorry, slice and swipe had the most, followed by volume cube and then Yea Big Yea High. And that's likely with the imprecision of having to move to activate it. Many times they would activate it and then essentially undo because it wasn't cutting exactly where they wanted.
So, no more questions? Thanks, Bret, again.